Welcome back. This is Unit 5. We're going to start out taking a look at a few more things with the periodic table. First of all, we look at the overall structure of the periodic table, okay? And we kind of drew an outline. You'll have to do this for your next test. I drew an outline of the periodic table. But we have a really important thing on the periodic table. It's called the stair step. And we look, and it's a dark blue line that runs through here. And the periodic table may be a dark black line. But we separate the elements here with that what we call stair step. So the way we do this is we say everything to the left of that stair step, these are all metals, okay? All right, as we have in our diagram here, everything to the left of the stair step are metals. Everything to the right are non-metals, okay? Everything to the right are non-metals. And we have the properties of metals that we'll talk about a little bit later. But everything that touches the stair step, so it would be boron, aluminum, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine, those are all called metalloids. And they have properties of both metal and a non-metal. Now, you're going to hear a lot about these in your lifetime, a lot of big discoveries happening. Of course, we know aluminum is not a metal and it's not a non-metal. That gives it the light weight that we use for airplanes. Silicone, we're beginning to see a lot of uses for silicone. Arsenic is actually rat poisoning. It's an interesting combination of a metal and a non-metal. So one of the things we'll start out, we'll talk about this a lot more, but you need to be able to draw an outline of the periodic table showing where the metals are at, the non-metals, and the metalloids. Now, as we begin to look at these different things, we realize that we have electrons and we have protons. Electrons have negative charges, protons have positive charges. Well, it's important for us to know that light charges repel each other. Light charges repel. So if I have two electrons, two negatives, and they come together, they're going to repel each other. Okay? Light charges repel. Unlike charges attract. So if I have a proton here that's a plus charge and an electron that's a minus charge, they're going to attract. They're going to pull themselves in. The other thing that we begin to look at in this chapter is we look at this, we look at colors, we look at wavelengths, we look at frequencies. So first of all, let's start out by defining a wavelength. So I draw a wave here, okay? There's three parts to a wave. The very top part of this wave, this is called the crest, okay? So we have a crest. Every time we have a wave, we have a crest. The top of the wave is the crest, the bottom of the wave is the trough. From crest to crest, this is the wavelength. Now, we give that a Greek symbol here. The wavelength symbol looks like this, okay? Now, and we draw it, it's kind of like here and down. The name of that symbol is lambda. Okay, so whenever we do wavelength, we use the symbol. I'll ask you on your test what's the symbol for wavelength, and you'll put this symbol, and the name for it is lambda. So we'll calculate a lot of wavelengths, and so as we look at frequency and we look at wavelength, frequency is a number of waves that pass by a given point in a given time. So I want to know what the frequency of a wave is. I want to know how many times it passes by in a certain time. Well, what we have is we have big long waves, and then we have little short waves. Okay, so we'll talk about that. And then we have something called the continuous spectrum. When we say continuous spectrum, we mean the spectrum of light in there that shows visible colors. Okay, so it's the wavelength of visible light colors. So when we see, and you've probably had this before, but when we see the colors of the rainbow, Roy G. Biv, okay, maybe you've had this, maybe you've not, but you have red, orange, yellow, green, blue, indigo, and violet. So what happens is that they're all different wavelengths. And so as we look at this, once again, Roy G. Biv, those are the possible colors. All the other colors are a combination of colors. So when we talk about the colors, the visible colors that we see, once again, that's called the continuous spectrum. Now, the short wavelength colors are red. So it's kind of interesting because this is a neat deal because this is the order that they go. So red, orange, yellow. So the short wavelength, what that means is that those waves are traveling, those waves are short and they're kind of intense. So when we see a red wave, we're seeing this. And it's just those little bitty short waves, much more intense. As they come at you, okay, your brain is actually trying to figure out the wavelength crest to crest. So when a red light is coming at you, you look and you notice it because it's really intense. The long wavelength is blue, okay? The blue, the indigo, the violet, okay? So on this end of the spectrum, that's a long wavelength. So that's this nice big wave that's coming in through here, okay? And it's a big wave that comes in. And it's actually really very relaxing to the eyes. because we can measure that wavelength and we can look at blue and we can say, oh, that's really cool because our eyes are not getting the intensity that they're getting for red. As a matter of fact, a lot of psychological studies showing that blue is a very calming color, whereas red is a very intense color. And this is where I like to stop and talk about the bullfighters. And so what happens is cows are actually colorblind. They actually can't see the colors. But what's interesting is when we throw a red cape out in front of a bull, the light that's reflected back is so intense that it bothers the bull. The bull doesn't like it. It actually annoys the bull, so the bull chases that. So here's our red cape, and we put it in the face of the bull, and the intensity is so much, okay, that it bothers the bull. It's kind of like you're walking down the street, and somebody has a neon red light, and it's like, oh, I noticed the light. The reason you notice it is it's actually annoying. You actually, when you look, you have to try to measure the intensity, and here comes this light. Boom, 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 and you're trying to pick up the wavelength. So you notice the neon light. The bull notices the red cape because the intensity is not pleasant for his eyes. So if I was a bullfighter, I would get a blue cape. Okay, I would get a blue cape. Now it would be my luck, it would just be a mean bull and it would chase me anyway. But in terms of colors, okay, the red is the short spectrum. The blue is the nice long spectrum. Now, as we move on, we're going to give you some general information in this chapter that we're going to tie in a little bit later, okay? And wavelength is a big, big thing. It's important for electrons, it's important for chemicals, and it's also important for what we call atomic spectra that we'll get to. Now, let's also look, we talked a little bit about the periodic table here. Let's review one thing. The atomic number tells us the electrons and protons. We had that earlier. So on the periodic table, like hydrogen is number 1, that tells us the number of, once again, the electrons and the protons, okay? So nitrogen's atomic number 7, so it has 7 electrons, 7 protons. But then we have another number called the atomic mass number. Now, the atomic mass number is what 1 mole of that weighs. We'll talk about a mole a little bit later. So here we go. So that number is going to be a decimal number because it's going to be an actual weight. So carbon has an atomic number of 6, but the mass number is 12.011. Nitrogen, the mass number, 14.0047. Now, the atomic mass number represents the protons and the neutrons. So when we want to find the number of neutrons, we'll subtract the mass number minus the atomic number. Okay? So for example, let's do carbon. Okay? So let's do carbon. Let's round these off. Okay? So the mass number for carbon, when we look, it's 12.011. So we're going to round that off to the nearest whole number. Okay? So once again, this is 0.0. If it was 0.5, we would round it up. Okay, so carbon is 12 for the mass number, okay, minus 6 for the atomic number, which means it has 6 neutrons. Okay, so once again, to get the number of neutrons, we subtract the mass number minus the atomic number. So then again, if we were to draw that particular atom, okay, so we were to draw the neutrons and the protons, we have the nucleus on the inside. Okay, so we look at carbon, we say, how many protons? Well, the atomic number is 6, so it's going to be 6 protons. How many neutrons? Well, the mass number was 12. The atomic number was 6, so it had 6 neutrons, okay? And then how many electrons are there in the outer shell? Well, once again, we get the electrons from the atomic number, because the atomic number tells us the electrons and protons. So in that case, carbon, the atomic number is 6, so we would have 6 electrons, okay? So once again, now we know, and we're going to get to more and more of this development of the electrons and development of the atoms, but right now we just we learned how to calculate the number of neutrons. Now, let's move over to the other board, okay? Now, everything that we showed you on the periodic table there is in the